Welcome everyone, thank you for coming. My name is Shlomi Noach, and this is CAP Theorem, not what we thought it was, not what we are looking for. And before I explain exactly what we're going to talk in the next 40 minutes, allow me to describe myself and my role at my company. So I'm with the database infrastructure team at GitHub. We deal with all sorts of databases. I work mostly with and around MySQL on all things availability and performance and scalability and internal tooling. And I author a bunch of open source projects in the MySQL ecosystem, one of which is called Orchestrator, which runs our high availability setup at GitHub. I'm assuming the people here are familiar with GitHub and what we do. We recently published, we have like 3 million organizations. Just in the past year, 44 million repos were created. The numbers are staggering. And while we store your actually repositories within Git, we store all the metadata on MySQL. So all your organizations, users, issues, pull requests, reviews, comments, etc., all of this, as well as the metadata on Git itself, right? Every commit and every push, everything is stored in MySQL. So it's a critical path in GitHub's availability. And indeed, you might argue that perhaps my most important role at GitHub is to make sure the databases are up and running and available so that the GitHub service is available to you and you can push and commit and comment and open issues and close issues. Does that make sense? Cool. So two incidents or two scenarios. One was a blog post I published on the GitHub Engineering blog describing how we run high availability for our MySQL setups. And the other was a famous, or maybe infamous, outage we had roughly 1 year ago. We had a split brain scenario. It took some time to recover, and we published a root cause analysis post for this. And both these posts sparkled some community discussion. And we saw a lot of questions like, why did you choose availability over consistency? Or according to CAP, you can't achieve that kind of consistency because you chose this path. And other CAP-related questions and statements. And I felt some of those were misleading or incorrect, but I couldn't put my finger on it. And I've been doing databases for nearly two decades now, and for a long time, the CAP Theorem was a little bit mystic and mythical to me. And so I took the time to dive into the CAP Theorem, and I was a little bit surprised with what I found, and I'd like to share that with you today. And with the concept of back to fundamentals, what I'd like to do today is formally define the terms and conditions of the CAP Theorem, prove it mathematically with you, but then try and investigate and look into the proof process and the proof and the terms and conditions and see how they match or do not match our engineering expectations. Right? Real world expectations. We will then try to extrapolate a little bit, to extend CAP or go beyond CAP to see if we can do better work in adapting CAP into our real world engineering practices. So, is that good? Cool. Who in this room has ever heard of CAP Theorem? If you've been to the last, to the previous session, you have. Okay, good. So, basically, if you don't, it's like, you know, you can have fast food, you can have cheap food, and you can have quality food. You can't have all three. Pick at most 2 out of 3. It's that kind of concept. Originally suggested by Professor Eric Brewer, that was like 20 years ago. He projected that a system can have 3 properties: consistency or strong consistency, high availability, and partition tolerance. And you may only pick 2 out of 3. You cannot build a system that consistently provides all 3 properties. And a couple of years later, Lynch and Gilbert published a paper, which is today known as the CAP Theorem. Right? It's a formal mathematical proof of something that is not exactly the CAP conjecture. My first assessment for today is that the CAP conjecture and the CAP theorem disagree with each other on some terms, namely definition of availability. The two use different terms for what availability means. And if you studied math, you know that in math, you change the slightest detail, everything falls apart, right? In math, you have to be very precise. So we're going to look into that shortly. So the terms and conditions of the CAP theorem, right? We're going to discuss the theorem for now, and later we'll touch the CAP conjecture. So we have consistency, we have availability, we have partition tolerance. Consistency is strong consistency, also called atomic consistency or linearizability. It's like perhaps the strictest form of consistency we can demand. It basically means once I've written some data into node number 1 in a distributed system, if that information was written and acknowledged and the commit said, yeah, okay, good, I go and try and read that piece of data on any other node, they must reflect that change of information or anything that comes later than that. So if I'm writing to one node, I'm updating some database table, I'm updating 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I've just written the number 7. I go and make a read on any other node. I should see 7 or 8 or 9 or 10, but definitely not 5 or 6. Does that make sense? Availability is where the CAP theorem disagrees with CAP conjecture. The definition of availability according to the CAP theorem is every request received by a non-failing node in the system must result in a response. I'll say it again. Every request received by a non-failing node in the system must result in a response. So there's a few corollary, follow-ups to that. So that means the request must return in a finite amount of time. It doesn't matter how long, it could take 3 days. It doesn't matter to the mathematical proof. And it must return without an error. And the last part is partition tolerance, means that should network break in some way, packets get lost, our system should be able to continue on operating. And the theme is that partition tolerance is beyond our control, right? Network partition is beyond our control because things happen and networks break. And so this is something we have to take into account. This is, if we design a system that cannot tolerate network partitioning, partition is going to break, so what's the point of a system that can handle it? It's going to happen. And so we must choose between availability and consistency in face of network partitioning. It's often described differently. If the network is okay, you can get both availability and consistency. But if the network breaks, you might need to choose between availability and consistency. So discussion is mostly between AP and CP systems. And let's prove the CAP theorem right now. This is basically the same proof as in Lynch and Gilbert's paper. So given 2 nodes, these are 2 database servers, and they replicate from each other. And they're in sync, and everyone's happy. We're going to place an infinite network partition between the 2 nodes, infinite in time. This network partition begins now and never ever completes. We're now going to write some data into node number 1. Let's say we write the word hello into node number 1. Let us assume that the system is available. Based on that assumption, my write will complete in a finite amount of time. Okay? Once my write completes, I will go to node number 2 and issue a read on that piece of data. Again, we assume that the system is available. Therefore, my read is going to complete in a finite amount of time. Now, during that time, the network was broken. It was broken for infinity. There was no way for node number 2 to get the value hello from node number 1. We assumed availability, and what we got as a result is inconsistency. The 2 nodes have different data. Node number 1 has the word hello, node number 2 does not. That's it. Does that make sense? It's simple enough, right? Did it feel very mathematical to you? No equations, but this is a formal mathematical proof. It's formal because of multiple reasons. I'll name two. One is that, it's the tiny details. If I say that I write something to node 1 and then read it from node 2, I can't say the words and then unless the amount of time spent on the write was finite. Because if that were infinite, how do you do something after an infinite amount of time? So, small details. Also, a classic proof by example or by counterexample, right? This proof presents a scenario where the network is broken and availability means inconsistency. So to clarify, CAP theorem doesn't say that you cannot get availability and consistency at the same time. It says you cannot design a system where you will be certain, where you can guarantee that availability and consistency will coexist at all times. Sometimes something's got to give, and the CAP theorem presented one example where that has to break. Okay, so far? Cool. All purple dragons can fly. Are people familiar with this kind of statement? Cool. In math, this is vacuous truth. It is a statement made on an empty set of objects. All purple dragons can fly is a true statement. To prove me wrong, you're going to have to show me a purple dragon that cannot fly. But there are no purple dragons. So this is vacuously true that all purple dragons can fly. We can do a lot of nice things with vacuous truth. All purple dragons can fly faster than the speed of light. Mathematically, this statement is true. Now, we understand that in no way were there such purple dragons. There's no way they could fly, waving their wings, and fly faster than the speed of light. But mathematically, this is sound. Moreover, all purple dragons can answer questions, and all purple dragons cannot answer questions. These seemingly contradicting statements are both true at the very same time. It would take a purple dragon to disprove at least one of those statements. But there are no purple dragons. So why am I talking about vacuous truth? Every request received by a non-failing node in the system must result in a response. So by vacuous truth, if all my nodes in the system are broken or failing, my system is available. That's the definition of availability according to the CAP theorem. So here's my idea. I work at GitHub, I work on databases. I'm going to go back and say to my team, hey, I've got the solution to availability. I'm going to crash all my database servers. So a perfectly honest question to this honorable crowd, perfectly honest question. Who here believes that by crashing all my database servers, I'm going to make the GitHub service more available to you, or indeed at all available to you? Raise your hand.
Just want to spot the mathematicians.
Right. Cool. So for the record, for people watching this on video, no one raised their hands, and with good reason. This doesn't make sense, right? And I claim that this definition of availability per CAP theorem, it doesn't make sense to me as an engineer. This is not what I perceive to be a definition of availability. I reject that definition. This is not how we should talk about availability. Let's talk about infinite network partitioning. Again, honest question. Has anyone ever seen an infinite network partition? Again, no one raises their hand. And with good reason. We've all wandered this earth for a finite amount of years. None of us has been able to see an infinite network partition. But if you'll indulge me, I'd like to illustrate this further. So I'd like you to meet Anna and Ben. They're SREs at their company. Oh, hi. So one day, Anna's attention is drawn to what seems to be an unfolding crisis. Oh dear. Ben, are you seeing what I'm seeing? The two investigate. It seems like our Virginia router is malfunctioning. Confirmed with the data center, they saw some smoke and then it burned. It's literally melted. So our Virginia DC is now network isolated. You know what that means? Oh, wow. The router is never coming back. This is an infinite network partition. We will never have consistency, ever again. There's just no point in anything. CAP Theorem proves this. For eternity. We may as well enjoy our time. We can live a life of adventure. We can go to Paris. We can go to Roma. We can go to DevOpsDays Tel Aviv. Hooray! Enters Carmen, their CDO. Well, hi everyone. So what's going on? Seems like we have an outage. Our VGA router burst up in flames. It is gone. For eternity. We now have an infinite network partitioning. We will never again have consistency. There's just no point in anything. CAP Theorem proves this. Can we expense travel to DevOpsDays Tel Aviv? Now, at this point, we feel that something is off, right? Something is terribly wrong in this story. But fortunately, Carmen is a practical CDO. Ben, yeah, here's my corporate credit card. I'd like you to go to the store downtown, buy a new router, take it to our Virginia data center, and replace the old router. Yeah, that also works. So what's even an infinite network partition? This isn't something we even plan for. This isn't something that interests us as engineers. We're interested in the network going down for an hour or two. We're not planning to solve an infinite network partition. This is an unrealistic scenario. Okay, fine. Why do I insist? But what if the network went down for a week? That's as good as infinite, right? Surely there's some number after which we can call this infinite. So can we just say long enough? Sure, we can say long enough, but the CAP theorem would break. The math would not work. Say the network broke down for 1 hour. All I need to do is when I read data from node number 2 is to sleep for 1 hour, then maybe a couple more seconds, wait out the network partition, read the data, hooray, I have consistency. Sure, you might say, well, a request that takes over an hour is as good as malfunctioning, right? It's not going to work out. So shouldn't we also put a time limit on the request time or the response time? Sure, that can be done. In fact, we can rephrase and rewrite the CAP theorem using time-limited constraints. If we say that the network could go down for up to time t, and we also require that response times are less than half t, then we can rephrase and reprove the CAP theorem along the very same lines. Say the network partition is limited to 1 hour, but response times must return below a half hour. So again, we write to node number 1, a half hour goes by, we read from node number 2, a half hour goes by, the network is still down for the next few milliseconds, and we have inconsistency. So let's call this the time-limited CAP. Is that okay? I should be happy now? I'm still not happy. I have 2 problems with time-limited CAP. First, I'm not sure why we need this t and half t. Why did we impose these specific metrics? Does that make sense engineering-wise? Maybe it does, but it feels to me like we have a solution and we're trying to find a problem that will nicely fit that solution. That's my first problem. But the second problem, which is my bigger one, is that I think it's a fallacy to continue down that path, because we still use the definition of availability that doesn't make sense to me as an engineer. I think it's a fallacy. I reject that definition. I think we should not proceed down that specific path. So let's look again at the CAP conjecture. CAP conjecture says a completely different thing. It defines availability as high availability. Data is considered highly available if a given consumer of the data can always reach some replica. In other words, equals the definition, but in simpler terms, I make a request, there's going to be at least one server that can respond to my request in a timely manner, in a finite amount of time. That sounds a lot more like the availability that I imagine as an engineer. It makes more sense to me. But to elaborate a little bit on how exactly different the CAP theorem and the CAP conjecture definitions of availability are, according to the CAP conjecture, not all nodes must respond in a finite amount of time. There just needs to be at least one, and there's going to be at least one. CAP theorem demands that all non-crashing nodes, all of them, will be able to respond in a finite amount of time. These two definitions do not contain one another. They're not, neither of them is stronger than the other. And I maintain that the CAP theorem does not prove the CAP theorem does not prove the CAP conjecture. So there's multiple ways to go from here. I'd like to look into the definition of CAP conjecture's high availability. And there's multiple trajectories from here. And I'd like to address the number of nodes in the system. You'll remember that the proof of CAP theorem addressed the scenario of 2 nodes. Now that is nice, but in real life we have more than 2 nodes. And so let's look at an n node scenario. So again, according to the CAP conjecture, let's assume that CAP conjecture checks out. Consumer always has access to data via at least one replica. So some node will be able to serve us. By the way, it does not require that this will be a different node than the one we wrote to. We may well be just speaking to that same node. So am I happy with that? It's better. It's something I can live with. It makes more sense to me, but not in practice. Because in practice, if I'm now the owner of databases at GitHub, there's some data sets we just can't serve off a single server, right? It's just not enough. We will need a fleet of servers. And so CAP is also short of capacity. And if there's anything I'm proud of in this presentation, it's this pun. And so I've trademarked it, and I'm sorry, you cannot use it. This is mine, and mine alone. So I'm going to conveniently move into the realm of quorum. So what if we changed at least one server able to respond to my request? What if we change this to the majority of the servers, right? What if we say something stronger than CAP conjecture? Majority of servers are able to respond to my requests. So this is not an accident that I picked majority, because I would like to take another look at CAP through consensus algorithms such as Paxos Raft and variations of the two, because there's variations. And so depending on the algorithm and depending on the variation, Paxos and Raft can guarantee that if a quorum of the servers, if the majority of the servers are alive, up and running, and connected, then writes are either consistent across nodes, or at least made durable across nodes, so that like the changelog is shipped, and maybe at a later stage we'll see the data. So these are pretty strong guarantees. And raise your hand if you are working with some system that uses Paxos or Raft. Good. If you're working with Kubernetes, it uses etcd, which uses Raft. If you work with Consul, it uses Raft. There's a few MySQL clusters working with Paxos. There's a variety of systems today that work with consensus algorithms. And so, do these consensus algorithms contradict CAP in any way? And the answer is no. I mean, yes, or depends how you want to look at it. They really play along with CAP, but first we need to understand how CAP works with n greater than 2. If we wanted to look at the proof again, but not with 2 nodes, but with 5 nodes, what would it look like? Does the network partition need to be around each and every server, or should there be like, I don't know, 2 slices of the network? Well, it turns out that the CAP theorem is so aggressive and so greedy that it's enough that you make a single network partition across a single or 2 servers, or it doesn't matter. As long as there is some network partition, CAP theorem says, yeah, you have a problem now. Because CAP demands that all known crash nodes will be able to serve your data, and it maintains that it will have to be either available or consistent. But with consensus-based algorithms, with enough rack diversity, with enough availability zones diversity, geo-distribution, we can have reasonable confidence that at any given time, reasonable, not total, reasonable confidence that at any given time, we will have a majority of our servers interconnected, up and running. We do that, we live with that reasonable confidence even while we're all here today. And given that, that subset of servers, that subset of majority of servers that are interconnected, up and running, provide availability and consistency at the same time. Now, it's a trick because it's the subset of the servers, right? There's still those other servers, and we need to push back into the application to know better than to query those servers. Or maybe, there's the InnoDB cluster implementations in MySQL actually can require those servers to crash themselves as soon as they are out of the consensus, so that no client can ever contact them, and this solves the consistency problem. But we're pretty happy with this solution, with that kind of a solution. We're satisfied, which conveniently leads me to my next observation. So the recap was that CAP doesn't say that you can't have availability and consistency at the same time. It says you can't guarantee to have them both at the same time at all times, right? Sometimes there will be a scenario where that will break. The proof presented such a scenario that I think is not very realistic, but there might be other scenarios as well. When we talk about, so CAP is really absolute about this. When we talk about high availability, the way you and I normally practice it in our work, we talk about nines, right? We talk about, is my service up and running? Is the web page responding? Does the page load? Right? Those kind of availability constraints. And we commonly measure high availability in nines. We say our service is available 3 nines, 4 nines, 5 nines. 5 nines is pretty good, right? People are really happy when their service is 5 nines available. That means like 5 minutes per year outage, which is a lot, right? 5 minutes, there could be millions of requests failing during those 5 minutes, and yet we're happy, we're good, yeah, we're 5 nines. And we understand that we cannot get 100%, and we understand that any additional 9 is going to cost more and more money, more and more efforts, and is error prone. And so we're content in stopping at some point and saying, yes, we're available enough. So why is it that with high availability, we're pragmatic, and we're okay to lose sometimes, but we are so obsessed with CAP theorem, you can never do this or that, because there could be scenarios where both cannot be achieved? What I would like to see is a nines equivalent model in CAP. Now, to be fair, Brewer predicted that in his first paper, and he reiterated that years later, that there might be a weaker CAP model where you will have partial availability or partial consistency. But that model has not been proved. What we still quote today is the CAP Theorem, which uses absolutism and uses scenarios that do not exist in our physical world. And we wave and say, according to CAP, this is impossible. And did you not hear about the CAP principle? This is impossible. Moreover, CAP is a subset. Availability and consistency and partition tolerance are important attributes of a distributed system, but they're not the only important aspects of distributed systems. There's a myriad of other things I can look into when building a distributed database system. And when I'm designing a system, it's not all about CAP. If people ask you, why did you design an AP system? Well, there's a lot of other considerations when I'm building my system. These are not the only things I think about, right? And so I strongly believe that while the trade-off exists, we understand as engineers, yeah, the network went down. You know, if you allow the write here and the network is still down, the data is not in the other node, we get inconsistent. We understand that concept. But CAP is not the model that we're looking for to solve, to save us, or to, you know, to formalize that problem or mission statement. And I maintain that we need to look into different models. The internet is full of misconceptions about CAP. Whether I'm right or wrong about my analysis doesn't matter, because if you search the internet, you will find so many contradictions between different articles, all trying to interpret the CAP theorem. Mine is yet another interpretation, but you will surely see those contradictions. Just by way of identifying these, try to see how many of these define availability according to the actual terms in the papers. So here is an assortment of links that are either authoritative or, as I believe to be, a very good and correct analysis and interpretation of the CAP theorem. And with that, I would like to thank this kind audience for your attention. And we have a few minutes for questions. What was the crisis I talked about? October 21, a day to remember. Last year we had, we had a data center network isolation because of reasons. We failed over, you know, in Hebrew it's tzalash or tarash. It's like you win or you lose. Like the system operated perfectly. We failed over to the other data center, but we couldn't operate in that data center because reasons. And we had to fail back, during which time, as expected, the original data center diverted. We got split brain between the original data center and the failed over DC. And so there were 40 seconds during which the old data center kept getting updates. And those are the 40 seconds of divergence. But the decision to roll back was made like after 20-ish, maybe 25 minutes. And so we said, yeah, we would rather preserve those 25 minutes as opposed to those 30 seconds, which meant we had to rebuild or roll back all those 40 seconds. It took us many hours to roll back. So yeah, it was a very infamous outage. It took well over 24 hours, unfortunately. Since then, we've built quite a few interesting mechanisms to prevent this in the future. So for example, in my world of MySQL, we actually created a time machine for MySQL. So next time that I hope that won't come, we will have multiple mechanisms before that. But if all else fails, we actually have a mechanism to roll back MySQL to previous point in time. So interesting stuff came out. Very good. Thank you very much. Enjoy lunch.